Hello, my dear students, and welcome to the final part with our first chapter dealing with the operational amplifiers. In this chapter, we are going to determine the operational amplifier circuits by two interesting circuits. The first is the differentiator, and the second is the integrator using op-amps. Now, let me start sharing my presentation slides and start the final part in this lecture. Okay, so now you can see my presentation slides and as well as my laser pointer, and let's start together this final part with operational amplifier chapter. In the previous part, we have discussed two very important circuits. The first is what's called the voltage follower, or what we call it, the buffer circuit. This circuit is usually used to isolate the input source to the load so that you can carry out the voltage without any loading effect. And we discuss in detail how this circuit works. Then we turn to another circuit, which is the differential or the difference amplifier, where we have two inputs, one inserted to the inverting input and the other is inserted to the non-inverting input. We have introduced together what's called by the common gain and the differential gain, and generally what's called the common mode rejection ratio, or the CMRR, as the ratio between the differential gain and the common gain. We have also showed the condition at which we can reduce the common mode gain to reach zero and maximize the differential gain to be R2 over R1. Then we also demonstrate together the input impedance of this structure, and we have concluded together that this is the main weak point of the structure, that its input impedance is 2R1, which is, or generally R1 plus R3, which is inversely proportional to the gain. So whenever you increase the input impedance or the input resistance, you will decrease the differential gain. Thus, this is a very important point. And in order to avoid this point, my dear student, in industry, we are usually use this isolated differential amplifier. As you can see, this second stage is typically a normal differential amplifier where you have one input to the inverting terminal and the second is to the non-inverting terminal. So if you cut the circuit here and see this right-hand side portion, you will find that this is typically the same like this one. But what we have made now is that we introduce a buffer or a voltage follower before or in between the input stage and the differential amplifier stage. Again, the buffer is used here to isolate the input with respect to the output. So this is a function of these two buffers or these two voltage followers in the starting or in the entrance stage of the circuit. We call this the instrumentational amplifier, because this is most probably the amplifier used in most of the instrumentational or instrumentation circuits. Another question I proposed maybe in the end of the previous lecture, if you remember, my dear student, in the previous part, is why we are using a closed loop circuit in order to demonstrate a difference amplifier. The question is very simple. Here in this circuit, we have two inputs, and the output is R2 minus R1 times V2 minus V1, which is the differential input, if you remember the differential input. However, without all these circuits, we can demonstrate the same behavior using the open loop configuration, if you remember the open loop configuration. In the open loop configuration, we have A output, V output equals A, V2 minus V1. which is typically the same like what we have reached in the difference amplifier, where instead of this open loop gain A, we have the differential gain, which is R2 over R1. So why we should use this complicated differential circuit in order to make a differential amplifier? And we already have the same output can be concluded using the open loop gain. The answer actually is very easy, my dear students. The answer is here, is what's called that output saturation. Let me start to demonstrate this idea. Okay, so I think you now can see my perfect. Okay. In the open loop configuration, we have something like this. This is V1, sorry, and this is V2. And the output, V out, equals A V2 minus V1. Perfect. Which is actually the same when we have this differential structure. So this is V1. And this is R1, this is R2, I don't know, R3, R4, and V2, and now the output equal a differential, which is R2 over R1, times V2 minus V1. So in these two cases, you get the same relation. V output is proportional to V2 minus V1 times gain. This is the open loop gain, and this is the differential. So why you should use this one and don't use this one? No, because this is more simpler. You will not use resistance and all this stuff. Why we should use the below one and not this one? This is due to what's called the saturation effect. If you remember, when we first introduced the operational amplifier, we introduced two terminals, which is the VCC terminal and the negative VCC terminal. And I told you that these are the supplies for the operational amplifier. So let's have an example. If the input signal, sorry, if this VCC and negative VCC are 15 volts and negative 15 volts. Okay, perfect. And let's assume that you have V2 equals 0.5 volts and V1 equals, for example, 0.1 volt. So V2 minus V1 will result with 0.5 minus 0.1, which is 0.4. Perfect. And let's assume that this gain, or this gain, is equals to 10. Very easy. You will tell me that 10 times 0.4, then the output is 4 volts. Perfect. Very easy and very simple. But what if this gain is 100? Then this 0.4 times 100 will be equal to 40. Does the output terminal will produce 40? The answer will be no, because principally the output voltage is not able to generate any voltage greater than or smaller than the supply. The output should be in this range. So whenever you have 0.4 with gain 10, the output will be 15, not 40. Because 0.4 times 10 is 40, but it's saturated to 15, then the output will be 15. Then this is basically what we call the output saturation. Again to our question. Then, based on this description, why this one is more preferable than this? The answer is very easy. Because here, the gain is controllable. But here, the gain is not controllable. Here, the gain, or the open loop gain, is a very high number. So usually, whenever you insert any input, you will reach the saturation. However, here you can control the gain. You can adjust R2 and R1 in order to make the gain level acceptable with the input level and the supply level. And this is why we use generally closed loop configuration rather than the open loop configuration, because in the closed loop configuration, we have the ability to control the gain whatever, however, in the open loop configuration, we don't have this ability to control the gain. This is very important note for you. So back to the presentation slides. Again, let's open the pointer. Now this is the saturation level. As you can see, this saturation level is from negative VCC to positive VCC. So your gain is granted whenever it's in this range. However, whenever you go to above or below this range, you will have a saturated out, and this is basically the saturation. So you can see it here, this clipped sinusoidal signal, because it's outside the saturation range. So outside, sorry, the linear range. So it is now in the saturation range, or what's called the output saturation. Okay, now let's go to the final two circuits. I believe these are two very easy circuits for you to solve. What's called the integrator and the differentiator. Both are very, very famous in the operational amplifier technology. So let's start first with the integrator circuit. Okay, so we have our operational amplifier as usual. This is negative and this is positive. Okay, we have a resistance, and then we have this input. So this is V in, and let's call this R in or R, whatever you want. And this is grounded as usual. And now, instead of have a feedback resistance, we have a feedback capacitor, and then we have that. As usual, what we are seeking for is a relation between the V output and the V input, as usual. If you have a good memory, you will recognize that this is typically the same like the inverting configuration, except of having a capacitor instead of a resistor, typically this. So let's do our 5 assumptions. Output impedance, input impedance is equal to 0, so no current is flowing inside the operational amplifier. Output resistance or impedance is equal to 0. Open loop gain is equal to infinity. So V positive equal to V negative, which means that this point is a virtual ground. As far as this point is a virtual ground, then the current flowing here, let me call it IN. This IN is equals to Vin minus 0 over Rin, or simply it's Vn over Rin. Okay, so how we can continue, my dear students? Okay, now the current flowing in this Rin resistance, which I call it IM, this current, have 2 options. Either to go to the operational amplifier, which is impossible because this is an ideal operational amplifier, or to flow to the capacitor, to charge a capacitor. So knowing that no current is flowing inside the operational amplifier, we can easily say that all the current flowing in this Rin resistance, which I call it IN, will go to the capacitor, will move here, or will flow to this capacitor. So let's call this, for example, IC or whatever. So the current IN equals to the current IC. Now, what is the current flowing inside the capacitor? We have to go back to our circuits module. We know that the current in the capacitor equals to C, which is the capacitance, dV by dt, where this V, what I call VC, is a voltage drop on the capacitor. What is a voltage drop on the capacitor? It's 0 minus V out. It's true, it's 0 minus V out. This is the voltage drop on the capacitor. So basically this minus C dV out by dt. So you have the first current equals to V in over I Rn, and you have the second current equals minus C dV out by dt. Very easy. You can just equalize these two currents together. That's right. So V in over Rn equals to minus C dV out by dt. What we are seeking for is a relation between V out and V in. So dV out by dt equals minus 1 over RC times V in. Or what you can say that V out equals to minus 1 over RC integration of the V in dt. So in order to get rid from this differentiation, what you did, let me make line here. What you did is simply you integrate both sides. So V out equals minus 1 over RC integration of V in dt. That's why we call this circuit, my dear students, is an integrator circuit, because you integrate the input. The output is the integration of the input with a factor equals to minus 1 over RC. Again, the negative signs appear because the input is connected to the inverting terminal, like what we did in the first circuit with the inverting configuration. So this what we call, my dear students, the integrating operational amplifier. Of course, it's obvious to say that whenever you have this circuit, you should have an AC signal, because basically if you have a DC signal, then you don't have a capacitor. Capacitor is open circuit whenever the voltage is DC, so this is not a closed loop configuration. And of course, whenever you have a capacity, whenever you have an AC signal or a time-dependent signal, you can use this operational amplifier configuration. Okay, let me turn to the second and the final example in this chapter. What we are going to do is just to replace the capacitor and the resistance. That's all. So negative, positive, ground. Now the capacitor is here. This is V in, and the resistance is here. This is R. This is not only different, very straightforward. So we are going to do the same procedure. This voltage equal to this, so this is virtual ground. The current flowing here I equals to 0. So the same 5 assumptions. Now the current flowing here, let me call it IC, will equal to the current flowing in the resistance, which is RR. This is V out. So the current flowing in the resistance is equal to what, my dear students? Is equals to 0, which is the virtual ground point, minus V out over R. So the IR is equals to 0 minus V out over R. And what about the current flowing in the capacitor? Similarly, it's IC equals C dV by dt. Which V is the voltage drop on the capacitor? What is the voltage drop on the capacitor? It's Vn minus 0. So IC will equals to C times dVn by dt. So now let's link these two equations, because IC equals to IR, as no current is flowing inside the operational amplifier, so the current here will go directly there. Accordingly, minus V out over R equals to C dVn by dt. Or what we can say that V out equals minus RC dVn by dt. As you see now, the output is the differentiation of the input. That's why we call this a differentiator circuit. And we have again a negative sign, my dear student, because this input is connected to the inverting terminal. So as you can see, it's very easy, straightforward, two circuits that can be widely used in various applications. You will see these two circuits, my dear students, may be in your ADC, analog digital converters, and DACs, the DAC, digital converters, as well as other applications where you need either to make any form of differentiation or integration to your inputs. Now, this is the termination for chapter number 1 under the title Operational Amplifier. In the next week, we are going to start a next chapter dealing with what's called the PN junction or the DACs. Again, we have already studied the PN junction in our solid state course, but from a semiconductor physics perspective. Now it's the turn to make it from a circuit perspective. Thank you very much for your concentration, and see you inshallah in the next week with the next chapter inshallah. Thank you.